Behind me is a video of the Bakun Hydroelectric Dam in Sarawak, Malaysia. It's a pretty cool place. Look at the beautiful view. What is a hydroelectric dam? In this video, we are going to discuss an past year question example, okay? And also think carefully about how the day-to-day energy that we have, giving us internet and computer, and its impact on the environment. Since I can't bring you there, I shall use Google Maps, all right? So the Bakun Hydroelectric Dam is located in Sarawak, which is a state in Malaysia. Go Google Sarawak. It's one of the most beautiful place in the world. Hashtag not biased Malaysian, all right? So shout out if you're from Sarawak. Anyway, this is the hydro dam, okay? It is connected to the Rajang the river. So if you come from a different country, maybe your country will have a different hydro dam, okay? Depending on where the rivers in your country are at. So as I zoom out a bit, you will notice that the Rajang River is actually pretty long, all right? It connects all the way, okay, I'm sorry for the internet lag, but it connects all the way, okay? And rivers have many, many roles in civilization, but we're not here to talk about that. So consider the fact that there's a hydro dam here. And what a hydro dam does, or hydroelectric dam does, is that it converts the kinetic energy of the water flowing in the river through various systems so that we can generate electricity. This is a form of renewable energy. But just because it's renewable doesn't always mean that it's good for the environment, because we will have to cut down a lot of forests along the way. And also cause some flooding at this region. This question is from Winter 11 Paper 2-1. And first, you're asked to distinguish between gravitational potential energy and electric potential energy. All right. So whenever you see the types of energy and you're asked to differentiate them, writing the definition will be a good starting point. Okay. So think of gravitational potential energy. It is related to an object or a mass that is moving inside a gravitational field. And because of the word potential, whenever you see the word potential, it is a form of stored energy. All right. So let's write down gravitational potential energy first. We can say this is that GPE is the energy stored, okay, when there is work done. When moving, what do we move? A mass in a gravitational field. So let's say you move the mass either up or down. This is all gravitational potential energy. What about electric potential energy? Well, electric potential energy can follow the same sentence, but the only difference is currently we are not moving a mass. We are moving a charge. Okay, so electric field is a field that we set up that will interact with the charge. Just like gravitational field is a field that we set up that will interact with a mass. So we can say that this one is the energy stored due to work done when the charge is moved. CHARG, charge is moved in a electric field. Or you could copy back the same sentence. Just replace the word mass with charge and gravitational field with electric field. All right. Okay, so this is good enough. Generally, we are looking for the comparison that looks like this. So each statement is 1 mark. Okay, next. A body of mass m moves vertically through a distance h. Okay, there's m moving vertically through a distance h near the Earth's surface. So Why do they emphasize Earth's surface? And why are we asked to compare electric potential energy and gravitational potential energy? More of gravitational field and electric field in your A2 syllabus. Stay tuned. Okay, remember that these two things are kind of really similar, but not really at the same time. But in this case, we are going back to your AS content. So right now, your mass is going to move vertically. Your M is here. Okay, we're going to move M vertically upwards to here. Okay, because we're going to move through a distance h near the Earth's surface. Okay, so is it under the influence of the Earth's gravitational field? Duh, teacher. Of course, gravity is going to pull the mass down, correct? So I will say work done. So it says here, use the defining equation for work done. What's the defining equation for work done? Work done is equal to Fs. You must write this. You must start with this. And the second thing is, you should also tell us that whenever there is work done, there is change in energy. So work done is equal to change, triangle means change, in gravitational potential energy. So hence, putting them together, change in GPE is equal to Fs. Okay? And the force here is mg. Because in order to move the weight up at constant speed, I need this F to be the same as the weight mg. So that only GPE change. KE constant. Okay, so we don't want the block to move faster or move slower, so cannot have net force. So the upward force must be the same as the downward force. Because if not, then work done is equal to change in KE plus change in GPE, which is a bit annoying. So we kind of don't do this one. Okay, that's why your KE constant. All right, so we're going to have this mg, that will be our force, F is equal to mg, and the distance traveled is h. So you have mg h. All right, so where are the marks? If you write W is equal to Fs, and substitute F is equal to mg, you get 1 mark. And finally, you relate the change in energy or the energy conversion. This part here, change in GPE is equal to Fs, leading to this one, you will get 1. Okay, so make sure you show all the key steps. Derivation of KE, GPE, elastic potential energy, all those you need to know. They could ask you for 2 to 3 marks. All right, but let us move on to the main part of the question, which is your hydro dam. Look at this hydro dam, so pretty. All right, so we have water inside a reservoir, and it will flow downstream as how river flows from the mountains downstream into the ocean, like you can see from the Google map. So go and find the hydro dam nearest to your house. Which hydro dam, if any, supplies energy to your country, to you, to your house, so that you can watch the channel, watch the video. All right, so the water that's flowing down will rotate the water wheel. Okay, will cause this water wheel to turn. Okay, and the water falls through a vertical height of 120 meters. Gravitational potential energy is converted to different forms of energy, including kinetic energy of the water. So you can imagine as the water flow downstream, it will flow faster and faster, but there's a lot of friction because, you know, the water can collide with the fish lah, the rock lah, who knows what else is inside the river, random boat, right? So at the water wheel, the kinetic energy of the water is only 10% of its GPE. All right, so show that the speed of the water as it reaches the wheel is 15 meters per second. So that means at the wheel, the kinetic energy is only 10% of the change in GPE of the water as the water flows downhill. Hiya, only 10% left. It's not very efficient. Well, what to do? So 10% is 0.1, and change in GPE is mg delta h. Delta H here is 120. And you go like, but teacher, I don't have mass there. I don't know how much water flow down. Trust yourself. What you don't have, you don't need. Because kinetic energy is half mv squared. Teacher, is this change in kinetic energy? Yes, but we are just going to make the assumption that by the time the water wheel rotates, or the kinetic energy of the water, before the water flow downstream, the water is essentially still. So the initial KE is assumed to be 0. Not that you have any information also, you don't have ma. So we assume that the kinetic energy is 0 because maybe the water here is still. So or rather, actually, I don't really. Basically, just don't know any information about the initial condition. So we are just saying that when it reaches the wheel, it's 15 meters per second. After that, we don't know it. All right. So I guess just half mv squared. But the amount of water is the same. The water that flows down is the same. So we have same mass. You can cancel off m. And finally, I will have v squared is equal to 2 times 0.1, okay, times 9.81. Change in height is 120. So we can press our calculator and find v. This will be 15.3 meter per second, or more or less 15 meter per second. Proven. All right. So right now, what is going on is when the water flow down, this change in KE, that is 10% of a GPE, the initial condition is assumed to be 0. So let's see. Initial is here. All right, my bad, not here. The wheel is the final position. So I'm going to assume that at this point here, the KE is 0. Because it's a reservoir, all the water is inside. Reservoir means like a place to store all the water. We assume a water stored in a container, like a reservoir, the speed is 0. Okay, and then the water begin to accelerate down. This one, if you want to, can minus 0. All right, but the answer remains the same. Okay, so you don't really need to know the mass because the amount of water falling down is the same amount of water that has the gain in KE. Okay, part 2. Part 2. The rotating water wheel is used to produce 110 kilowatt of electric power. Okay, so just now what we had was GPE. Here, GPE, convert to KE. Only 10% of the GPE left. Okay, and that KE will convert to electrical energy. So what we're having now is GPE to KE. But 90% is lost. So this is 10%. 90% is lost. Heat, collision, sound. River can be quite noisy, right? Okay. And kinetic energy is now going to convert to electrical energy. Okay. So let's continue to read the question. We have 110 kilowatt of electric power. This is the output. Electrical energy. Calculate the mass of water flowing per second through the wheel. So basically, they're asking us to find what is mass per second. Okay, mass per second, so mass per unit time. Assuming that the production of electrical energy from kinetic energy, okay, so KE to electrical energy, so electrical energy from kinetic energy is 25% efficient. Wait, so this one, 25% and 100%, so 75 is wasted. Well, teacher, this hydro dam not very efficient. Oh. Here, 10% left. And then after that, we lose another 75%. So only 25% of the 10% is left. GG. Okay, so, but it's okay, you know, still energy. All right. So right now, 25% efficient. So first things first, I want to think about when this is 25% efficient, okay, what kind of ratio are we doing, right? So efficiency can be written as output, the useful output over input power times 100%. Okay. So because this is 0.25, this is the ratio of output to input. But what is output? Output is electrical energy because you're converting. So I know this one is 110 kilowatt. Okay. And what is your input? Input is kinetic energy. But they are talking about power. So the input power is actually the change in kinetic energy divided by time. Okay, so we're going to assume that the 15 meter per second water wheel rotation thing is all converted zero. Eventually, the water wheel will stop rotating. All right, so this one will be half mv square divided by t. Oh, I see something. Okay, or rather, maybe instead of substituting this way, I find the input power first lah. All right, so in here, the input power is 440 times 10 to the power of 3. Okay, so this is 440 times 10 to the power of 3. Change in KE is half mv squared divided by T. You see the M over T here, mass per unit time, which is what we're looking for. So right now, I will rearrange the equation. Half will bring up to multiply 880 times 10 to the power of 3. Okay, divided by V squared. And V is 15. We just found V just now in the previous part of the question. You want to use 15 also can. You want to use 15.3 also can. I'm going to stick to 15.3 because it's more accurate. Slightly more accurate. Squared. All right. So this is equal to M over T. Let's look at the unit kg per second. So we can press our calculators to find the value for this one, which will get me 3759. So M over T is 3759. You want to round to 2SF. You can put this one as 3800. Okay. So 3800 kg per second because everybody is SI. All right. So where are the marks? First things first, if you can identify that the power is actually, the input power is rate of change of kinetic energy, this part will get C1 already. Here to here, this part here. All right. And then after that, let me look at the mark scheme. You substitute the other values. You find 440 and you plug it into this equation. Here, the substitution is 1 mark. This one and this one. Leading to the final answer. Okay. So in this question, right, whenever you see efficiency, highly encourage you to think about the changes in energy. Okay, so currently KE is converted to electrical energy and only 25% is left. All right, so if you steady and you think about power as work done over time or change in energy over time, you'll be okay. There are a lot of assumptions that we make. For example, we assume that all the KE is expressed in the rotation of the water wheel. Teacher, how does water wheel make electrical energy, convert to electrical energy? Here we use a dynamo. So if you know what's a dynamo, you remember this from your high school days, that's great. We rotate a coil in a magnetic field. If not, we will learn this in your A2 as well. So this entire question is a sneak peek into the stuff that you will learn in your A2 physics. But for the meantime, understand that efficiency is just a ratio. And at every single step of the conversion, some energy is lost. Do it one thing at a time. Okay. One last footnote that I want to mention is sometimes students ask me, teacher, why I must use change in KE over time? Why can't I use T is FV? So I'll write here. Why cannot input power is equal to FV? Well, this V here is this velocity of the water? Because this v here should be the speed of the rotation, right? So in this case, right, this v, we don't know the speed of turbine. Of course, you are going to ask me, but teacher, what about 15? Okay, 15 is related, this 15, okay, let me change highlight color. This 15 is related to the kinetic energy of the water. So I can use 15 meter per second or 15.3 meter per second because that is the kinetic energy of water. But it is not the speed of rotation of the wheel. Okay, the wheel is not rotating at 15 meter per second. Makes no sense, right? So this one should be the speed of the turbine, but no info. Don't know. No information. We don't know the rotational speed of the turbine, so we cannot use. Okay, so the reason why we cannot use this is because we don't know this. And also, what's the force on the turbine? Not enough information. So whenever you want to use P is equal to Fv, this V have to be the speed of that object itself. It's because currently what is happening is the Ke of the water will rotate the wheel. Okay, because the wheel will flow through the water and cause rotation. But only 25% of that Ke is electrical energy. So I can use that Ke as a starting point. But this 15 meter per second is water, not turbine, or not the wheel. So cannot, no? And this one must be speed of the wheel. Okay, so hope that answers some of you who may be thinking, why can't we P equal to Fp? This is a very specific equation. Force must be constant, and also V must be the V of the object itself, not any simple V you can take. All right, that's it. I'll see you in the next video. Bye-bye.